In less than a month, NASA is going to launch a machine that could quietly rewrite everything we think we understand about the universe. It's not hunting for aliens. It's not looking for a ninth planet. It's hunting for proof that could either confirm our entire model of reality or blow it apart. This is the Nancy Grace Roman Space Telescope, and by the time it finishes its first 5 years of work, it will have captured more of the sky than Hubble managed in 3 decades. Here's what it's actually going to find, and why some scientists are quietly bracing for the results to break the rulebook. Mark the date, August 30th, 2026. That's when Roman lifts off from Launch Complex 39A at Kennedy Space Center, the same pad that launched Apollo 11, riding a SpaceX Falcon Heavy rocket. This mission has been in the works for over a decade. It started life under a much less exciting name, the Wide Field Infrared Survey Telescope. Somewhere along the way, NASA renamed it after a woman most people have never heard of, but we'll get to her, because her story is honestly one of the best parts of this whole mission. Here's the part that should surprise you. This telescope is arriving 9 months ahead of schedule. In an industry where delayed is basically the default setting, where the James Webb Telescope launched over a decade late, Roman showing up early is almost unheard of. Something this ambitious, this expensive, moving faster than planned. That alone tells you NASA is treating this as a priority mission, not a side project. Now, if you're thinking, wait, didn't we already get a giant new telescope with Webb? You're right. And understanding how Roman is different is actually the key to understanding why this mission matters so much. Think of it like camera lenses. James Webb is a telephoto lens. It zooms incredibly close to single objects, one galaxy, one exoplanet atmosphere, one tiny patch of the ancient universe, and captures jaw-dropping detail. But it's slow. Pointing Webb at one target can take hours or days. Hubble was our first real wide-angle lens in space. Revolutionary for its time, but still, compared to what's coming, narrow. Imagine trying to photograph the entire coastline of a country, one postage stamp-sized photo at a time. Roman is the wide-angle lens on steroids. Same size mirror as Hubble 2.4 meters, but paired with a 300 megapixel camera and a field of view that's at least 100 times larger than Hubble's. Some comparisons against Hubble's infrared camera specifically put that number above 200 times. Here's the analogy that makes it click. Astronomers have shown what a single Roman image would look like laid over the Andromeda Galaxy. Hubble's entire field of view fits inside it like a single tile in a massive mosaic. One Roman exposure could contain dozens of full Hubble images stitched together in one shot. That's not a minor upgrade. That's a different category of instrument. NASA has been explicit that Roman and Webb are designed to work as a team. Roman surveys huge swaths of sky fast, flags the most interesting objects, a strange galaxy, a promising exoplanet signal, and then Webb swoops in for the close-up wide net, then deep dive. Roman isn't replacing Hubble or Webb. It's the missing piece that makes both of them more powerful. Let's talk hardware, because the numbers on this thing are almost cartoonish. Fully deployed, Roman stretches about 42 feet long and 14 feet wide, roughly the size of a semi-truck trailer, just floating a million miles from Earth. Inside, it carries 2 major instruments. The first is the wide field instrument, that 300 megapixel eye we just talked about. For comparison, the camera in your phone is probably somewhere between 12 and 50 megapixels. Roman's camera outguns it by a factor of 6 to 25, and it's doing it while staring into deep space, not taking a selfie. The second is the coronagraph instrument, and this one is genuinely wild. Imagine trying to photograph a firefly sitting directly next to a lighthouse beam. That's basically the problem of trying to directly photograph a planet next to its host star. The star's glare is billions of times brighter and just drowns the planet out. The coronagraph is built to physically block out that starlight, like holding your thumb up to blot out the sun, so the instrument can catch the much fainter light reflecting off a planet nearby. It's designed to directly image Jupiter-sized worlds and the dusty debris disks around nearby stars. No telescope has attempted this at this scale before. Put those 2 instruments together and you get a machine that can survey enormous swaths of the sky and zoom in for direct portraits of alien worlds. The raw number, 0.28 square degrees, means nothing to most people. The full moon in our night sky covers about 0.2 square degrees. That means a single Roman exposure covers more sky than the full moon in one shot. With Hubble-level sharpness, Hubble in its wide field mode would need dozens of separate pointings stitched together just to match that one frame. Getting Roman built was hard enough. Getting it safely into position is its own kind of terrifying. If you remember the James Webb Telescope launch back in 2021, you might remember the phrase 29 days of terror. Webb had to unfold itself using over 300 individual mechanisms, any one of which could have failed and doomed the entire multi-billion-dollar mission. NASA engineers spent that entire month barely breathing. Roman's deployment is, thankfully, a lot less nerve-wracking, but it's not nothing. Within about an hour of launch, Roman unfolds a sun shield to start protecting its instruments from heat. Then, one at a time, 4 solar panels swing open, each one taking about 30 seconds, with a 30-second pause between each while 2 more panels stay fixed in place. A protective visor-like cover deploys separately. Later, a high-gain antenna unfolds, the same antenna that will eventually be responsible for beaming back that flood of data we're about to talk about. It's a shorter list of critical steps than Webb faced. But make no mistake, this is still a machine unfolding itself in the vacuum of space, a million miles from the nearest repair technician. There is no second chance from launch. Roman spends roughly the next 100 days traveling to and settling into its final home. The Sun-Earth L2 point, positioned so Earth never blocks its view and its instruments stay in permanent, stable shadow. During that same window, engineers are running the telescope through checkouts and calibration. That means humanity's first real science-grade images from Roman likely won't arrive until sometime around late 2026 into early 2027. Then a fire hose of data unlike anything astronomy has ever handled. Speaking of that fire hose, let's talk numbers, because this is where things get almost absurd. Once fully operational, Roman is expected to send back roughly 1 terabyte of data every single day, beamed across nearly 1 million miles of empty space. Picture streaming 1 million songs back-to-back nonstop every single day for years. That's the scale we're talking about. Over its first 5 years alone, Roman is projected to capture 50 times more images than Hubble captured in 3 decades of operation. 1 month of Roman surveying our galaxy could cover more ground than Hubble managed in an entire century. Here's the problem that creates: no human being could ever look at all of it. Not one person, not a team of 1,000 people. The volume is simply too large for human eyes to review directly. So a huge share of the searching, hunting for the faint blip of a supernova, the telltale flicker of a hidden exoplanet, the subtle bending of light around invisible mass is going to fall to machine learning algorithms, combing through billions of data points for patterns no person could catch by eye. In a very real sense, artificial intelligence is going to be one of Roman's most important instruments, even though it's not bolted onto the telescope itself. Okay, here's the part that actually explains why this mission could rewrite the textbooks. Roman isn't just taking pretty pictures, it's built around 3 specific deliberate hunts called its core community surveys. Roman is going to map the shapes and positions of more than 1 billion galaxies. Why does that matter? Because dark matter, the invisible material that outweighs all the regular matter in the universe combined, doesn't emit light. We can't see it directly. We only know it exists because its gravity subtly warps and bends the light from galaxies behind it, an effect called gravitational lensing. By measuring that warping across 1 billion galaxies, scientists can essentially build a 3D map of where all the invisible mass in the universe is actually sitting. Nobody has ever attempted this at this scale. This survey works differently. It points at the same patch of sky over and over, stitching the images together like frames of a movie to catch objects that change over time. Exploding stars called Type Ia supernovae. Roman is expected to catch on the order of 10,000 of these explosions. Here's why that's huge. These particular supernovae explode with a remarkably consistent brightness, which means astronomers can use them like cosmic mile markers to measure exactly how fast the universe is expanding, and whether that expansion rate has changed over billions of years. Quick history lesson, because this connects directly to why Roman matters. It was this exact technique, measuring distant Type Ia supernovae, that first revealed back in 1998 that the universe's expansion isn't just continuing, it's accelerating. That discovery was so shocking it won the Nobel Prize in Physics, and it's the entire reason dark energy entered our vocabulary in the first place. We still don't know what dark energy actually is. We just know something is pushing galaxies apart faster and faster, and we've been trying to pin it down with better data ever since. Roman is about to supercharge that hunt. Instead of the hundreds of distant supernovae earlier surveys managed to catch, Roman's haul of roughly 10,000 could become the largest, most precise dataset on dark energy ever assembled. Enough to finally tell us whether that mysterious push has stayed constant since the beginning or whether it's changing over cosmic time. This is arguably the wildest of the 3 Roman is going to stare unblinking at the dense, crowded center of our own Milky Way galaxy, watching hundreds of millions of stars for years. It's hunting for a phenomenon called gravitational microlensing. When one star happens to pass directly in front of another, its gravity briefly acts like a natural magnifying glass, causing the background star to flash brighter for a short window of time. If the foreground star happens to have planets orbiting it, those planets create their own tiny secondary flickers in that brightness spike. This technique can catch planets that basically every other method misses. Compare it to the 2 techniques that found most known exoplanets so far. The transit method, used by Kepler, which watches for a planet dimming its star as it crosses in front, great for planets orbiting close in, nearly blind to anything farther out. And the radial velocity method, which watches a star wobble from a planet's gravity, powerful, but biased toward big, heavy planets close to their star. Microlensing doesn't care about any of that. It can catch planets far from their star, planets barely bigger than Earth, even rogue planets with no host star at all, just drifting alone through the galaxy untethered to anything. It can even detect isolated black holes wandering through space with nothing else giving them away, because even invisible objects still bend light with their gravity. The catch, each microlensing event is a one-time flash. Once it happens, that exact alignment will likely never repeat in a human lifetime. So Roman has to watch continuously, patiently for years, waiting to catch each fleeting flicker as it happens. NASA's own projections estimate Roman could reveal signs of up to 200,000 potential exoplanets, more than every exoplanet ever discovered by every other mission combined many times over. Right now, after roughly 3 decades of exoplanet hunting by every telescope on and off the planet, we've confirmed a little under 6,000. Roman alone could dwarf that entire combined effort within its first 5 years. 3 surveys, 3 of the biggest open questions in physics. 1 telescope. Before we get to the big what if, you need to know who this telescope is actually named after, because her story is the most human part of this entire mission. Nancy Grace Roman was born in Nashville in 1925. From childhood, she was obsessed with the stars. She earned her astronomy degree from Swarthmore, then a PhD from the University of Chicago in 1949, in an era when she was routinely told flat out that a woman had no business in science. In her own words, describing how she was treated early in her career, she once said she was told from the beginning that women could not be scientists. She didn't listen. In 1959, Roman became NASA's first female executive, appointed as the agency's very first chief of astronomy. And in that role, she did something extraordinary. She spent years convincing a skeptical Congress and a budget-strapped NASA to fund an outrageous idea, a giant telescope floating above the atmosphere that could see the universe with a clarity no ground-based observatory ever could. That telescope became Hubble Roman, fought so hard to make it real that Hubble's own chief scientist nicknamed her the Mother of Hubble. She retired from NASA in 1979, but kept consulting on the Hubble project for years afterward. She passed away in 2018, at 93 years old, having spent her entire life proving wrong every person who told her she didn't belong in that room. Now, in 2026, her name is riding a rocket into space on a telescope built to finish the job she started, pushing our vision of the universe even further than Hubble ever could. Here's the question that keeps some scientists up at night. Everything modern cosmology is built on: the age of the universe, the existence of dark matter. The accelerating expansion driven by dark energy is called the standard model of cosmology, and it's held up remarkably well for decades. But it's still built on incomplete evidence. We've never had a dataset this large, this precise, covering this much of the sky, tracking dark matter and dark energy at the same time. If Roman's billion galaxy map and its 10,000 supernova dataset line up neatly with current predictions, that's a massive confirmation of everything we think we know. But if they don't line up, if the expansion rate doesn't match, if the dark matter distribution looks different than expected, that's not a footnote. That's a crack in the foundation of modern physics, and it would send cosmologists back to the drawing board on how the universe actually works. Either outcome is historic, there is no boring result here. And Roman won't be working alone. It joins a new generation of observatories built specifically to attack these questions from different angles, including the European Space Agency's Euclid telescope, already mapping dark matter and dark energy from space, and the Vera Rubin Observatory on the ground in Chile, which is photographing the entire visible sky on repeat, hunting for anything that changes or explodes. Scientists are planning to cross-check Roman's results against both. If multiple independent telescopes built by different teams, using different methods, all start pointing at the same crack in our current model of the universe, that's not a glitch, that's a discovery. So here's where we stand. In days, this telescope leaves Earth bound for a silent point in space nearly 1 million miles away. Roughly 100 days later, if everything goes right, it opens its eyes for real and starts sending back a terabyte of data a day, every day, for years. Somewhere in that flood of images could be the discovery that finally explains dark energy, or dark matter, or a hidden Earth-sized world drifting alone through the galaxy that no one has ever seen before. Or it could reveal something science never predicted at all. Named after a woman who was once told she didn't belong in this field, Roman is about to give humanity its widest, deepest, most complete view of the universe we've ever had. And for the first time in over 30 years, nobody, not even NASA, knows exactly what's about to look back. Subscribe. We'll be covering Roman's launch live on August 30th, and its first images the moment they arrive.